Alright guys, we're going to talk about section 3.2 today. So that's dealing with predictions, residuals, and interpreting a regression line. So to start out with this, let's look at a table here of your explanatory and response variables. So our explanatory, we're going to talk about the number of dark chocolates that you can eat, and the response, we're going to talk about the amount of calories you would get from these. So as you can see there, we have 1, 2, 3, 4, and we skip over 5, we're going to go 6 and 7, because we don't know what the number 5, how many calories it would give us. But for the calories for all those figures we have there, they're listed right there in the response. So let's go over to staplet.com and get our least squares regression line, as well as let's see what the plot looks like. All right, so we got it all right there in there already. Okay, so there is our scatter plot on the data right there. So again, we have the number of dark chocolates as our explanatory variable, and our response variable is the amount of calories. So let's come down here to calculate the least squares regression line to get an equation. So the equation it gives us is right here. Okay, so we get y hat equals 25.57143 plus 7.41615x. So with this, the y hat, that means predicted y value. So in this case, we are predicting the amount of calories, okay? So to write this out, is the predicted amount of calories equals 25.57143 plus 7.41615 times the number of chocolates. So we can use this equation to predict the amount of calories we would get if we ate 5 chocolates. So let's do that. So we're going to put a number 5 there for the number of chocolates and see what amount it gives us for the predicted amount of calories. So it gives us 62.6522. That means the predicted amount of calories for 5 pieces of dark chocolate is 62.6522 calories. So let's think about this. If we were to go in there and get the data of how many calories it was for exactly 5 pieces of dark chocolate, we can then compare it to our predicted amount. So we can simply say that, let's go ahead and say it was 59. So let's say we had 5 pieces of dark chocolate, and that actually gave us 59 calories. So what's the prediction for our 5 pieces of dark chocolate? Was it too high or too low, and by how much? So to do that, we're going to use our equation for the residual. So our equation for the residual is actual minus predicted. So in this case, our R value, our actual value was 59, and our predicted value was 62.6522. So if we subtract that, we get we should get negative 3.6522. So what does that mean about our predicted value? What that's telling us is that our predicted value was 3.6522 calories above the actual amount of calories gained by 5 pieces of chocolate. So it means our predicted calorie intake was 3.6522 too high. Now let's say you got a little hungry for some chocolate and you ate 50 pieces. What can you predict your calorie intake would be? Well, according to the equation there, we can simply take, so we're going to take 25.57143 plus our 7.41615 times 50, and that gives us 396.379 calories. Would you trust that prediction? I wouldn't trust the prediction because it is too far away on the x-axis off of our data to really verify that's how many calories exactly you're going to get from that many pieces of chocolate. So with that, this is called extrapolation. Because this is so far away on the x-axis, it's called extrapolation. With looking at our equation for the least squares regression line, what is our y-intercept of the equation and what does it mean? Well, our y-intercept of this is going to be our value right here. That's telling us when we eat 0 chocolate pieces, we will gain 25.57143 calories. Does that make sense? No, right? But according to our least squares regression line, that's the equation for our y-intercept. What is our slope of the equation and what does that mean? Our slope is 7.41615. What that means is when we eat 1 piece of dark chocolate, the amount of calories increases by 7.41615 calories. Okay, so now we're going to talk about least squares regression lines and residual plots for 3.2. So we have some data here for our iPhones and the year they came out and how many units were sold in millions. So let's take this data and put it in a Statlet and see what type of scatter plot we get. So we've got the data right here already listed for us. Again, our explanatory is a year, response is units sold. And there's our scatter plot. Now looking at that, what would you say the form is? Would you say the form is linear or non-linear? Hopefully you can see it is non-linear. Our form is making kind of a curve going along with those data points. So also let's look to see what our least squares regression line is. Least squares regression line is right here. Alright, so we have our least squares regression line, and that gives us those big numbers right there. And what is the y-hat telling us? Right, the y-hat is telling us predicted units sold. So it's telling us predicted units sold is equal to that equation, and in place of the x, we're going to substitute in the year for that to calculate how many units sold. So let's use this equation to predict units sold for each year, and then find the residual, the actual minus predicted, and see how that looks. Okay, so there are the calculations for all our predicted units sold in millions, and then the residual. Now let's go back and look at that residual plot that we had in Statlet. So here's the residual plot that is made from the least squares regression line. So with this, what it's telling us is, right here, these values above the actual was greater, and these below actual was less. So the next thing is that you want to take away from is this residual plot showing that the regression line is a good fit to the data? With this, I would say it's not, because the residual plot is actually giving a pattern, and you do not want to have a pattern in your residual plot. You want to have a scattered setup on your data points in your residual plot. Again, no, the residual plot looks curved, so the distribution was non-linear. In other words, the distribution that we saw in our scatter plot here is non-linear. It's showing a curved pattern, which is displayed in the residual plots themselves. So to sum it all up for dealing with least squares regression line and residual plots, we want to take the least squares regression line is the line with the smallest sum of residuals squared. And the residual plot, you want it to be scattered. It's good if it is scattered. However, if it forms a shape or any type of pattern, therefore it is bad for the residual plot. All right, guys, so we've learned a little bit about 3.2 to start out with, and I'll see you next time.